First of all, let me thank the organizers for the invitation and for organizing this very nice meeting. It's always a pleasure to be back to Lumini. As most of you know, in the last few years I've been studying problems of stability in suspension bridges, and also today's talk is somehow motivated by suspension bridges. This is just a small remark. Because we have instability in suspension bridges, and I believe that most of you saw what happened in the video of the sadly celebrated collapse of the Tacoma Narrows Bridge in 1940, which collapsed under several circumstances that we are going to analyze. But maybe not all of you know that this is not just an isolated event. This thing had occurred many other times. And you see there is one even more recent on the Matukituki Bridge in New Zealand in 1977. And well, if you're interested in this book, which was published last year, I devoted the whole first chapter to historical events and to a collection of what happened and the description of witnesses of these collapses. What do I mean by similar way? Similar way, I mean that torsional oscillations appeared, because the torsional oscillations are the enemies of the stability of bridges. So these are the destructive oscillation, while a bridge can withstand longitudinal oscillations. And this is precisely the conclusion that reached also the federal report that was done just after the collapse. And in the board there was also Theodor von Karman. As you may see, this is their conclusion, is that the torsional displacement oscillation is the one which led to the collapse. And therefore, of course, this leads to the question, why do torsional oscillations appear in bridges? So why does this instability manifest? And there have been many attempts to give an answer, mostly of aeroelastic type. And in the last few years, with several co-authors, we gave a new explanation in terms of structural problem. It's a structural instability, something which is within the structure. So this is going to be the starting point of my talk, although today I will not address this problem. On the contrary, I will address two other questions. That is there a way to measure the torsional performance of a bridge? So if you give me a bridge with all the parameters, can I tell you a priori if it's going to be a good bridge or not? And second question, is it possible to reduce the torsional oscillations in bridges, in some sense? Okay, last year, together with Alberto Ferrero, we introduced a model for suspension bridge, viewing the deck of the bridge as a thin rectangular plate. Yes, okay, this is a thin plate because you have to take into account all the ratios of the different measures. And if you compute the length, which we normalize to be pi, and the width, which we normalize to be 2L, the thickness is in such a way that it is neither a membrane nor a thick plate. It is precisely a thin plate. Okay, the deck is here hinged on these two edges. It is hinged, while these long edges are free. And if I put here some dark parts, is because here is where you have basically the restoring force due to the cables and the hangers. So the forces are mostly going to concentrate in these two strips, although the wind and the traffic loads can be spread everywhere. Okay, well, this is just a brief survey of what is known. According to the Kirchhoff-Love theory of elasticity, this is how you compute the energy of a bridge, and you see there is a quadratic part which consists in the bending energy and involves second-order derivatives, minus, of course, a linear part, which is the force which acts on the plate. Sigma that you see here is the Poisson ratio, and of course, if you are in suitable spaces, this part here disappears because you integrate by parts, and this is equal to 0. But in this case, since we have two free edges, this remains, and in particular, since we have free edges, we can neglect also the stretching energy. Then, well, even if sigma is, the realistic values are between 0 and 1/2, there are some foams or some particular foams that may have also negative Poisson ratio. In any case, for sigma between -1 and 1, this quadratic part is positive, so this function is a nice one. You have a convex quadratic part and minus a linear part, so in particular it has a unique minimizer. And we want to minimize it in this space, so this is second-order Sobolev space, with boundary conditions only on the two short edges. The other are free. Okay, then you endow this Hilbert space with a usual scalar product, I mean the natural scalar product, and of course, straightforward, use the Lax-Milgrom theorem, you get a unique solution, which is the unique minimizer of this energy. Here you can take F to be in the dual space, but this is going to discuss whether this is the best assumption. Okay, if you ever want to write it in a strong form, how do you get the strong form? So imagine that F is more regular. Well, you get here the biharmonic U equal to F, so this is a plate equation. The first set of boundary conditions is on the short edges, and these are hinged boundary conditions, the so-called Navier boundary conditions, while on the free edges you have these ugly boundary conditions of second and third order, which also involve the Poisson ratio. Here you see you have sigma and 2 minus sigma. Okay, there is a good, this is not so bad, because there is a good way to tackle this problem, in particular if F does not depend on Y, since the dependence on Y is very small, because Y itself is small. You can separate variables and can find an explicit solution through Fourier series. And this is because you have two opposite edges hinged. This was already in the original paper by Navier in 1823, Société Philomatique de France. And then it was taken again by Lévy, Zanaboni in 1940. And well, but these boundary conditions, the free ones, well, this is just an exercise, but they were never tackled before with these Fourier series methods. Okay, this is just some calculus. Okay, let's look at the vibrating modes, because we are interested in oscillations. So let's have a look at the eigenfunctions of the related problem. So you solve biharmonic U equal lambda U with the boundary conditions that we have seen. And basically, we find two families of eigenfunctions by separating variables. So we have one part which is sine mx. This gives you the number of oscillation in the longitudinal direction, multiplied by some complicated function. We have them explicitly, which only depend on y. They contain either hyperbolic or trigonometric sine and cosine. Well, they're a little bit tough. In any case, these are even and these are odd with respect to y. Remember, the plate is symmetric with respect to the x-axis. Okay, m measures, well, m minus 1 is the number of nodes that you have in the x direction, and k measures the number of nodes that you have in the y direction. Except that here you have to shift, because when it is even, the first one is, when k is equal 1 here, this is positive. Okay, so we have two classes, and in fact, the first one, since y is small, even means almost constant, and so it's of the kind sine mx, so this is a longitudinal eigenfunction, while if the one which are odd basically are of the kind of y sine mx. These are the torsional eigenfunctions, and this is a sketch of the picture, so this more or less is the first one that you get. This is the second one, it's a sine 2x, and this is the one having also a torsional component. Okay, so this is more or less how they look like. And of course, if we put the numbers, we have explicit forms of this. If we put numbers for sigma, the Poisson ratio, and L, we find all them explicitly. And the good choice is sigma equals 0.2, because this is a mixture of, the deck is a mixture of concrete and steel. And L, it's pi over 150, because if you think that the length to be 1 kilometer, then this is more or less 4 lanes, so it's slightly more than 12 meters. Okay, this is just an example. We made also other computation with different values of the parameters. Okay, so let's start with the first question. Can we measure the torsional performances of bridges when they are modeled with this model? And we recently gave an answer to this question together with Elvise Berchio and Davide Buoso, who is here. We tried to introduce a functional able to measure the torsional performances. So let's start with this problem here. And let's take f, even if you take f in h minus 2, then you're not allowed to write the strong form, but in any case, you find a solution which is in h2, and therefore it is continuous up to the boundary, because we are in dimension 2. And in particular, it is, the trace is well defined and is continuous, and we can compute what we call the gap function, so the gap that you have between the two free edges. You measure u of x on the top edge minus u of x on the bottom edge, and then you compute the maximum of this function. And this is perfectly defined because we are in H2 and in dimension 2. Of course, you have nothing similar for second-order problems or in higher dimensions because of this embedding which may fail. H1 does not embed into C0, not even in dimension 2. Okay, so this is our measure for the torsional performance of a bridge. And the first question is, of course, is this a good measure? This is our suggestion. So we made some toy examples to see if this works. And first of all, of course, the gap function, as you saw it here, it depends on f, so it depends on the load that you put on the plate. So first of all, you would like to normalize f in some space, and then to try to see what's going on for the corresponding gap function. And this is the first toy example. You take f, this is normalized in L1. You see is sine x, so just one sign in the longitudinal direction, and then there is an exponential, and this is a function which is always positive, and as alpha tends to infinity, it tends to concentrate on the upper edge. So we're pushing all the load on the upper edge, and in fact what you can prove is that this tends to a delta only in the y direction, concentrated on the upper edge, multiplied by some sine x. Okay, so this is what happens, and in particular we're interested in finding what is the behavior of the maximal gap for this, in the case you push this load on the upper edge. And here you can separate variables. We can compute explicitly the solution in terms, of course, of Fourier series. We can compute explicitly the gap function and the maximal gap. And then we have to give up, and we have to use computer to see what is the behavior of this gap function depending on alpha. So this is what we find. Again, we take sigma equals 0.2 and L equal pi over 150. So everything is done by hand except the plot. The plot, we put the function which depends on alpha in Mathematica, and this is what we get. As you see, this is in logarithmic scale. It is strictly increasing. So it means that if you push the load on the upper edge, this is going to increase the gap function. So it seems to be a good measure for the torsional performances. Then we made another experiment by taking the eigenfunctions, and so a resonant case, you take f to be an eigenfunction, but we take only the torsional eigenfunctions because these are the only ones which give a weight to the gap function. And we normalize them in L1, and we consider this problem here. Of course, the solution of this problem is itself an eigenfunction, because this is resonance with some constant in front. So again, we can compute explicitly this one. And this is what we get for the gap function in this case, again, when L equal pi over 150 sigma 0, 2. Okay, you do not have to learn by heart all these numbers, but just have a look at the main thing. The main thing is that if you move horizontally or vertically on these, in this table, you have strictly decreasing function. What are these tables? Here you have M, which measure the numbers of nodes in the x direction, and K, which measure the number of nodes in the y direction, which means that the worst situation is obtained when, let's say, you have the first eigenfunction, meaning by this that you have an odd eigenfunction with no zeros in the upper half plate and no zeros in the x direction. Okay, and so this is really what one expects, because what one expects this eigenfunction to be the worst one. So we were quite happy to say that, in fact, this is a good measure. And now that we have a good measure, we would like to answer to the main question of the talk. Can we do something to reduce the torsional oscillations and to improve the performances of a bridge? And we addressed this question together with Elvise Berchio, Davide Buoso, and Davide Zucco. He's also here. Well, this is a quite lengthy paper, and as you see, it gave the name to this talk, the challenging name that Nicola didn't like. Okay, and here, this is the main heart of the talk and of this, the talk. Okay, so we want to insert a strong material in an open subset of the plate, of a given measure. We have a certain amount of strong material. We want to insert it and to modify then this energy. And we're going to modify it by thinking that the strong material has some stiffness. And we take the characteristic function chi d to be put in the place where we want to stiffen the plate. But we're going to tackle the problem from two different points of view, very different from a physical point of view, but also from a mathematical point of view. The first case is the following. We strengthen the plate by putting, in some sense, by increasing the bending energy that you need to bend the plate. You see, if you want to bend the plate when you are in D, then you're going to pay more. And so this is going to increase the energy and to raise the value of the minimum. Okay? So this is the first way. This really means putting a stronger material inside the plate. And then there is another way, which is weakening the force. So instead of putting this term here, you put it here. And this means that you want to, let's say, to put some dampers or some aerodynamic shapes in the plate in order that the force, when the force hits in these places, it is less powerful. Okay? So this is the main difference from a physical point of view. But from a mathematical point of view, by the way, let me keep these two functionals, which I will need throughout, because these are the two functionals that I will consider. From a mathematical point of view, the difference is very subtle, because the first one, E1, if you put this guy here, then, of course, when you have a weak solution that you have straightforward, when you look minimizer, you have a weak form of this equation, but you have no strong solution because you cannot integrate by parts. There is a discontinuity in this term. On the other hand, if you take the other functional, well, you have troubles with the weak form if you take f in h minus 2, because you have to divide this f in h minus 2 by a discontinuous function. So roughly speaking, in the case of E1, we have no strong form. In the case of E2, we have no weak form. However, if f is more regular, and more regular means L1, L1 is enough. If it is in L1, you immediately have a strong form in the second case, and then you have to solve this strong elliptic equation. Okay? So both problems make sense, and we could find some results for each one of these problems. Okay, now this is the definition of the problem. We have to seek forces in some class capital F, and reinforcement in some classes capital D. And let's take F and D in these classes, and first we fix them, and then we find a minimizer. Of course, the minimizer of these two energies are in general different, so we're tackling two different problems. We have a minimizer which is continuous, we already said that, and therefore we can compute the gap function. So for any F in this space and D in this, well, set, we know that there is a maximal gap, which is this measure that we saw before. Then we let f vary, and we seek the worst f. So we seek what is the worst situation for the plate, which undergoes the maximal gap, because it's where you get the maximal torsion. And hopefully you have to solve this problem here, and this could have a solution. And once you found the worst f, then you let d vary, and d should vary among possible shapes. But then you're interested in minimizing this, because this is what you want to have, the minimal possible gap function, so you have the minimal torsion. So this is our minimax-max problem. And in fact, I forgot one minimum, because GFD comes out from a minimizer, so there should be a mini-max-max-min problem, but it would be too bad. Okay, so this is what we have to find, and is there something similar in literature? In fact, no. And the reason is that here we are taking traces which are continuous. However, the problem of strengthening material is well known, for instance, in the case of the torsion problem that we heard yesterday from Vandenberg. You take the torsion problem, and again, you want to put some strong material in order to, this is a different torsion problem. You want to measure the torsional resistance of a bar with cross-section omega, and then you put this, again, this reinforcement in here, and you want to find which is the best way to put this reinforcement inside the bar. And there is a paper which I studied many years ago together with Ilaria Fragala and Graziano Crasta, a very nice paper by Bernd Cavol, Stara, and Wittum, where they address the problem and they immediately realize that there is no solution and you are led to have homogenization. And for us, this is a bad word. We want to prevent homogenization, otherwise the engineer will not even look at our solution. There is also a parallel problem coming from, again, we want to have the basic frequency of a membrane to be as small as possible by putting a reinforcement. So this leads to an Euler-Lagrange equation that you see in this way. So you have an eigenvalue here, which with this weight in front of it, and you want to find the best D in order to minimize this eigenvalue. And these are works by Cianillo and Koenig. You see, this is slightly different from our problem. However, these were maybe the most related problems that we found. And of course, they have very little to do with our problem because you do not have this. We have a different cost function, basically. Okay, so let me recall it again, since this is the crucial slide of my talk, how we set up this mini-max-max problem. We first fix both F and D, and we compute the maximal gap that we have. Then we take the worst F, then we take the best D, and then we have to solve this problem here. Okay, so first of all, let's try to see what happens when we fix D and we move F. Okay, the first natural thing is to normalize F in H-2, but in that case, we only deal with functional E1, because E2, as I said, does not want to have F in H-2. And this problem has a solution. If you take any open set inside omega, you take the maximum of this function by letting vary F, it has a maximum. If you do the same thing in LP, in this case, both functionals are allowed, we can see that also in LP you can normalize and you have a solution, but you have to exclude p equal 1. This is somehow clear and expected, because if you have norm 1, you don't know what the sequence will converge to. But in any case, you also have a solution in this case. Okay, so these seem to give good classes, H-2 and LP. In fact, you cannot expect uniqueness, of course, because plus and minus F already generate the same gap function. And in fact, as I will show in a minute, in general, you also have worse problems of uniqueness. However, you should not expect uniqueness. Okay, now imagine that we do the opposite thing. So imagine that we know precisely what we have seen, so that for some D, we have always a minimizer. And then we want to minimize this among all possible varying D. And now we want to find suitable classes of D where this minimum problem admits a solution. And as I said, we want to avoid homogenization. So we're going to take very small classes. We're not just taking open sets, because otherwise we're immediately into trouble. And here are some suggestions. There are many others possible. So we will have the existence of a minimum when D, the capital D, is one of the following set classes. First time, cross-type reinforcements. So we take either horizontal or vertical arms reinforcing the plate in a finite number and with a minimal amplitude. This is not too difficult. What we call tiles of rectangular shape. So you take rectangles and you put them inside the plate, but with a minimal in radius in order not to them to shrink to a segment or even to a point. Or networks of bounded length, which means you take a line which has a finite one-dimensional house of measure and you fatten it by taking the epsilon tabular neighborhood, so you get a flat line, a fat line. And, well, these are the most general Lipschitzian trusses. We take with epsilon cone property. By this, we mean that we have a minimal amplitude, but also a minimal radius. So these are basically small triangles that you put inside on the boundary, and they have to fit inside. So for D, in any one of these classes, we know that there exists a minimizer. Okay, let's have a look at some symmetry results. I think that from a mathematical point of view, these are the most interesting results. But from a physical point of view and engineering point of view, maybe they are not. Because in bridges, engineers do not use symmetry. However, we are among mathematicians, so let's have a little fun with these symmetry results. And the first statement concerns, well, first let's introduce the spaces where of odd and even functions. This is quite simple in H2. Well, this is the usual definition, the usual way to decompose and to obtain the odd and even part of any function. These are continuous functions, remember. And we have that these two guys are orthogonal, and you have a direct sum of this space, the direct decomposition into these spaces. And also, we define the spaces of even and odd distributions, and you have to take when the duality is equal to 0 on the odd or even functions. Okay, so these are more or less standard definitions. And okay, so the first result is the following. Assume that D is symmetric with respect to the x-axis, means in the y direction you have symmetry. Then you can seek the maximum of this guy here only among functions which are, well, functions, distribution in this case, which are odd. So you only need to take these ones. So you restrict the class of admissible function in some sense. However, in this case, we for sure have no uniqueness because we have this other statement. It says that even if you find one which is odd, you find infinitely many others which are not odd and give you the same maximal gap. So this is really a case of non-uniqueness. You have many others which are not, you see, they have an even component. Okay, and of course, when speaking of h-2, I'm thinking of E1, of the functional E1. In LP, what happens in LP? Well, in LP, again, the maximum, when you normalize in LP, you exclude p equal 1. It's the maximum if you just take the odd functions. And then, but here you have a difference because, in fact, you have no minimizer which are not odd. Here they are necessarily odd. Sorry, maximizer. Any maximizer f of this problem here is necessarily odd. So you have really to rule out the functions f which are not odd. Okay, let's make some guesses. In the case where D is empty is a particular case of symmetric D. And here the guess is that in h-2, the maximal gap you get it when you have two deltas in these two places, of course, with opposite masses. You have to put the correct mass. So you put two deltas in the middle of the free edges. If you want to find the case of L infinity, this is the natural conjecture that you put +1, a load +1 on one side and -1 on the other side. Well, the first one is slightly more than a conjecture. We have some lemmas, but I mean, this is still a conjecture. Okay, but in LP, what is going to happen in LP, we have no idea. And the reason is that, morally, this is the minimizer in L1. Okay, because this is what you get when you have a minimizing sequence in L1. So this is any L infinity, and you expect in LP to be something in between these two. But what? For us, it's absolutely not clear. So what this could give for this maximum problem here, we have not even a conjecture. Okay, so let's see what happens in the case of cross-type reinforcements. So this is what we have the plate with. This is a case of just one cross. And in this situation, of course, you have to take care of all the measures. I will skip this painful part. So just some pictures. But in this case, we can separate variables. This is really tough because here we have to take into account the discontinuities which arise here. And now I'm dealing with case E2 because here we need the strong form. So this is the results now are dealing with the case E2. And then again, we take the same problem that we saw before for the free plate, and we push alpha to infinity. So we want to have the concentration on the upper edge of the plate. Okay? And we take different values of G. What kind of forms of G? What kind of G? Well, we took basically G equals sine x, sine nx. So again, looking like a trigonometric function. And then we took many vertical arms. So this is a shape. You have just one middle horizontal arm and many equidistributed vertical arms. Okay? And what we found is Okay, so we computed these vertical arms in number from n to 0 to 5. So 0 is no arms at all, and m from 1 to 10, so sine mx in that direction. And this is the problem that we solved. You see, this is the strong form related to the energy E2, okay, plus the boundary conditions. This is a particular example, and we tried many different examples. I will show you now the results in this particular situations, but what we find here is the very same thing for other values of n, m, which is the number of arms and of oscillations, and also of the amplitude of the arms. And well, we chose these parameters. And this is what we found. Again, don't learn by heart this table, but look what happens. Look at the first line. The first line is the gap, the maximal gap that you have for the free plate. And you see that in some cases, for instance here, 408, here you get 442. So if you put some stiffening, you get a worse performance. And there are cases where this is even worse. You see here you have 10, here you have 9. So why does this happen? Well, first of all, there are some trusses that aggravate the performance of the force. Why? Because there is a bad combination. If you strengthen only where the force, let's say, pushes upwards and not where it pushes downwards, then you will have a worse force. It's kind of taking the absolute value. You see, if you have sign changing, they compensate. So this tells us immediately that it is not true that any truss you put, you're going to get a better performance. Okay, in particular, these two values, 10 here, you see how huge this is compared with the other ones, in particular with 1 here and 9. Why are these so large? This is D3. So D3 for m equals 7 and m equals 9, why are they larger? Because we take sine 7x and sine 9x, they have the same sign in corresponding of the arms, of the vertical arms. So we are ruling out the contribution of the force in always having the same sign. So we get a worse performance. Of course, there's also good news that, in fact, each forcing terms has a good truss, and there is a pattern for this. You see, you should follow this diagonal. You see 47, then you go to 13, 158, 598. You go on this diagonal down here, which means that D2m minus 1, if you put these arms in a clever way, these are the ones which are going to give the best performance of the gap function. And there is a reason for this, because this is where the reinforcement is put precisely where the force attains a maximum or a minimum. Okay, this is all. You cannot find any rule, and you cannot find any monotonicity of G infinity. So, I mean, if you want to study this table and see something else, I mean, the main conclusion is that we must be very careful. It is not true that putting material necessarily leads to a better performance. Okay, then we tried some polygonal trusses. So let's consider just 4 classes of possible domains D. The first one are parallel rectangles strengthening the two edges, the two free edges of the plate. This maybe is the most natural thing which comes in mind, because this is the place where we have the restoring force. Then we put a large number of right isosceles triangles. These are not really isosceles, and this picture is misleading because there are in fact 75 or 90 of these triangles, so there are really many, many. But the total mass of these reinforcements are the same as the total mass that we put here. So we want to compare what happens in these two situations. And right triangles are really, well, the engineers use this shape, they mostly use this shape. Then we take squares, almost squares, because again we have to play a little bit with the width. And again we maintain the same measure for D. And this is used by engineers in pedestrian suspension bridges. This is what they usually take when you have not so many loads in the middle. And the last one is to prevent questions from Giuseppe Buttazzo, who certainly wants to know what happens when you have 2 pi over 3 angles. So we put hexagons, and the angles here are 2 pi over 3. But we only consider the case where this point, this bifurcation point, is in the middle of the plate, which is probably not the best position, but so far this is the only, well, maybe we'll try something more, but this is the result we have so far. Why this angle? Because, well, you know, in many irrigation problem or public transportation problem, these angles are optimal in some sense to carry some kind of load, which can be traffic load, or can be water, or can be a load on the deck of a bridge. Okay, then we compare these 4 trusses for when F is at resonance. F is at resonance, which means that we take a torsional eigenfunction, and then we solve the PDE, the strong PDE. Of course, now the solution is not going to be an eigenfunction, because you have this disturbance of that term. Okay, we have many computations. I will show you what we find everywhere. We always found this hierarchy here. So if you put no reinforcement, you get the worst performance. So it seems that on the vibrating modes, this is really improving if you put reinforcements. Then you have that the best reinforcements are the 2 strips on the 2 edges. Next, you have squares. Then you have these hexagons. And then you have triangles. And this is a first surprise, because one expects, in fact, hexagons to be, well, squares to be in between triangles and hexagons. But this is not the case. And even more, maybe playing a little bit with the position of this bifurcation point, maybe we can get that the hexagons go even below squares. In any case, this is what we found. And the bad news is that, in fact, triangles are the most usually by engineers. Okay, this is the new Tacoma bridges. There are 2 bridges now, and you see now here many right triangles being all aware. Of course, I'm cheating a little bit, because this is a 3-dimensional truss. It has many different performances, but still this is a shape that is quite commonly used by engineers. So if we are right, they're using the worst trusses, possible trusses. Of course, this is kind of a joke. I don't want to claim such a strong statement. Okay, so what remains to be done? Well, many things. There are many questions and many possible open problems and many conjectures to be solved. And I think that every day we find a new question which we would like to give an answer. We need to have a better feeling of the combination between F and D. This was really a surprise at the beginning. Then we found an explanation. But to see that so many bad things can happen, you wish to strengthen, and in fact you get a worse situation. And then to find maybe optimal classes, where do you have to minimize, in which space, and which kind of trusses you need to consider. Okay, thank you very much for your attention.